morning, everyone. After yesterday's more theoretical lecture on image processing, today Rafa will give a more practical overview of the workflow that people typically do to get from their micrographs all the way to their structure. So, Rafa?
Thank you, Shores. Good morning, everyone. So, over the last week and yesterday, we've been talking about the whole process of cryo-EM. And so by now you should be able to get your pieces and very well-behaved sample onto a grid and make a very nice grid, and you're able to optimize it and get a very nice distribution of your particles on the ice. And put it into a microscope, align it, and put it in conditions where you can obtain high-resolution information in your images. And then you can get those images, put it on a computer and process it in order to make a reconstruction of the object that you image in the microscope. So Shores yesterday went a little bit in detail on what happens behind the scenes with Relion and doing data processing. And what I'm going to do today is go through how can we get from the beginning to the end on a more practical way. So this slide just to stress again what are the problems that we have and that we need to solve in order to go from these 2D images that we get from the microscope to a 3D reconstruction from the object that we're imaging. And those problems are basically that we don't know the orientations of these images. The data is really noisy, so because of the radiation damage, we need to use very low dose, and so the data is noisy, and the synapse noise is very low. And the microscope is introducing artifacts in these images, and we also defocus in order to gain contrast. So if we can fix these problems, we can solve this, we can make a reconstruction of 3D structure. And for that, we need to correct for the CTF, we need to average over many, many images, and we need to find out what the orientations of those particles were when they were imaged in the microscope. And I will focus on how we do this with Relion and all the software that is wrapped into Relion. But there's obviously many other packages that can be used, and they work in similar ways, some of them, some in different ways. And you should always try and use different things. But we'll focus on Relion today. So this will be a typical overview of all the different steps that you should follow in order to go from the micrographs to the final map, and then go into interpretation of the map. And so I'll try to go through the different steps in a more practical way. So at the beginning, we'll look at the initial processing, which will involve correction of movement and correction of the CTF, manual picking of particles, initial to declassification, and later we'll talk about generation of initial model, 3D classification, and auto refinement. We'll discuss how we can do movie refinement and particle policy to account for particle movement and radiation damage within Relion. And then we'll discuss different approaches to treat heterogeneity in our samples. And finally, how to get your final map through post-processing and log resolution estimations. But before we start, let me just mention this briefly. And I think it's important. This is a bit specific for the LMB, but I guess it works for everywhere. That we're generating a lot of data, and resources for data storage and for computation are scarce, and especially if you have a lot of users. So everybody should be aware that we're generating a lot of data. This is just a particular example of one data set that I collected recently. But the point is that we generate very heavy movies that we don't need to put in our fast storage, and we can keep it in the slower storage servers and only move to the fast storage server, the data that we need. So movies, we shouldn't need, in most of the cases, to move over there. And that way, the whole system can keep working without interruptions for everyone. OK, so the first step after you've collected your images is to perform motion correction. So let's say we collected images with 40 electrons, total dose per Armstrong square. And so that would be a micrograph. But instead of collecting a still image, we collected a movie that contains many frames. In this case, it's 10 frames. And each of them will have 4 electrons per Armstrong square. But what really happens in the microscope is that the states will have a little bit of drift, and that the sample will actually move when the electrons are going through it. And that's called beam-induced movement. And what this will produce is that the image will look a bit blurred because of this movement. But because we're collecting these movies, we can use the different frames and try to align them back together and improve the signal. And by doing that, we can recover some of the information. And there's now many different softwares that can do this. Rely on wraps for unblurring motion core, so I'll talk about that, but there's other software that can deal with this. This blurring of the image is easily recognized by doing an FFT, and you can see this anisotropic behavior. And you can do this while you're collecting data. So I think the best way to fix this movement is by collecting as good data as possible in the first place, and not rely on the software to correct for things that you could have corrected before. But even in the best case, there will always be some movement that you need to correct for, and you should use this software to do it. This is an example of a ribosome data set where I just average a few of the first frames, a few of the last ones, and I'm playing a movie just swapping in between the two. And you can see the movement, the range of movement in between the beginning and the end of the movie. But after correction with motion core, you can see now that in the FFT that the tone rings go all the way to high resolution, and you can see that on the rotational averages. So this movement is corrected. Now in Reliant, motion core 2 and Ambler are wrapped, and you can use them directly from Reliant. You need to provide some parameters like pixel size. You can, at this stage, drop some of the frames if you would like, if you don't want to use all the frames in your movie. Although this is not recommended because particle polysins should be able to account for all the problems, and it will give you a better result. And with motion core, you can actually not correct only for the movement of the full frame, but use subdomains within your micrograph, and you can define that also within Reliant. This is, if you want to look at detail, you should refer to the documentation for motion core. And if you have collected super resolution data on the K2, you could also bin it right now in order to be able to process later. And you can group frames if you have very little signal, very little dose per frame at this stage. So after it's run, you need to check your results, and you can do that by looking at the log file. So Reliant will make a log file with plots from every micrograph, and they will look like this. So you have in X and Y direction the movement of every frame. So that would be the first, second, etc. And you can get an idea of how much movement was in your micrographs, and also get an idea whether motion correction has worked or there was a problem with it. One thing you can also do now with both motion core 2 and Unblur is account for radiation damage already at this stage. So if you, like you see here, as you image your sample, you will suffer from radiation damage from the electrons that are going through the sample. And you can see that the high resolution information is quickly lost. So in order to correct for this, you can compensate for this radiation, for this dose damage, so by a dose weighting. So you can do this now at the very beginning, at the micrograph level, by using a theoretical model that will weight the different frames. And you need to input the actual dose that you put on the sample. And so you need to be careful to actually write down what you've done during data collection. If you give a wrong value here, everything will be wrong. And nevertheless, this Reliant will take care of this as well during particle policing, and we'll talk about this later on. So after we've done this, we now have better images. They have been motion corrected, and we can do now CTF estimation in order to do CTF correction later. So as Paul explained nicely last week, in order to get contrast in our images, we are defocusing and relying on the imperfections of the microscope to provide this increased contrast. But this is also modifying our images with these aberrations, and we need to correct for them. So luckily, we can do that fairly easily by modeling the CTF of our images by finding the defocus and fitting this sinusoid curve that will explain the tone rings in the images. And there's many different software that do this. Again, Reliant wraps for CTF finite GCTF, and so you can use them from within, but you could use any software outside Reliant and then put your CTF information in. You need to provide the parameters from data collection from the microscope that you've used. You can restrict the searches for the different values of the defoci, and the software will find this. One note of caution is that if you use those weighting during motion correction, you should be aware that these images will have a dampened high resolution information. So when you do CTF estimation, you should use the non-dose weighted images in order to get a better estimation of this, because there's better signal. These are the type of results that you will get, and you can look at them, and in order to make sure that your fitting has worked, this is a result from CTF find, and you can see that's the signal, the amplitude of the signal, that's the fit. So you need to make sure that this is a correct fit. And you can do it also in a more graphical manner by displaying the CTF images with the model displayed here and the tone rings from your image there. So you should make sure that all of these fits all the way up to high resolution. And this will be the output from GCTF, where you can see the experimental data, a rotational average of your data, so you get a better signal in order to compare and the model. Now, this is just a general comment that every parameter that you put into Reliant and that Reliant calculates from your data is going to be put into these text files called star files. So there's always a header that will explain what is written in every one of those columns, and then every line will be containing information for either microns or particles. So you can always go into these files and look at the actual data and get information from it if you need to. Now, two more things about CTF estimation that I wanted to mention is, one is that now that software that can do per particle CTF estimation, this might come handy at some point. For instance, if you're doing tilted data collection, although there's also other software that does tilted data CTF estimation like CTF tilt. But so per particle CTF might improve your estimation of the CTF in many cases. And the other particular case that I wanted to mention is in the case of faceplate that are nowadays getting more common and people are using it more. And so one thing that happens with the faceplate data is that there's another parameter that we need to estimate, which is the phase shift. And you can see that, as Christos explained already, the phase shift will change over time while you're collecting. So as you put more electrons going through the faceplate, the phase shift will build up, giving you the extra contrast, but then this phase shift that is changing, you need to estimate for every micrograph. And now GCTF and CTF Find 4 can do this. And just as a quick note, for GCTF, you need to use amplitude contrast of 0, and you should limit the phase shift from 0 to 180. And with this, it should be fairly straightforward to estimate the phase shift for your faceplate data. And you actually go to the star file and plot this phase shift over time or over micrograph. You should see that behavior from the data collection for every time that you switch to a new position on the faceplate. So this might be useful to evaluate your data collection as well. Okay, so now we have corrected, or we have estimated the CTF information that we need for correction. And one thing that we should do now at this point is go through all our data set and check our images and really discard those that are not good enough for reconstruction. So you can do this easily in Reliant by using this subset selection job type, which will allow you to display all the images, for instance, all the CTF images, and select for them. And then you should go through them and find the ones that are problematic in order to discard it. So if you look at the CTF, this looks fine. The resolution estimation for GCTF is high, and you see the tone rings fit well, and there's no strange things happening here. So then if you look at the image looks good as well. So this is one image that you will keep. But sometimes you will start to see funny things on your CTF, and it's good to be able to know what they are, and it comes with experience. So it's always useful to look at both in parallel and find out what is really the problem. So in this one, you see some strong signal in this region, which corresponds with the water ring signal. So it's probably coming from ice. If you look at the image, it's actually not that obvious that there's ice in this image, but there's some that is getting these signals. And also there's some blurring because motion control hasn't been able to correct for all this beam-induced movement. So this, you should discard this image. This is very close to focus, so EPU clearly made a mistake here and collected an image very close to focus, and you cannot use this mainly because you don't see the particles, so what are you going to do with it? This is another image where you can see some strength signal also that will suggest some ice crystals, but then when you look at the image, you see that there's a big crystal on one part of the micrograph that is giving this signal, but the rest of the micrograph is fine, so you can still use this one. And again, another example of a bad micrograph where there's still a lot of beam-induced movement and drift, and you cannot use this one. More examples of how ice will look like, drift that motion core hasn't been able to correct, just will discard those images. Astigmatism can be corrected for provided the CTF estimation went well, and you have a good estimation of the foci and the angle in between the focus. And but you should look at this, and if you have high astigmatism in your data set, you should, next time you go to a microscope, you should be more careful with this and correct it before. And last but not least, you should make sure that in your images there's particles. And otherwise you might end up with problems. We can discuss this later. Okay, so we've already picked our, selected our micros. The next thing that we need to do is select the particles within the micros. This can be done manually, and this is fairly easy for big samples. So if you have a big protein or protein complex, it's going to be quite easy to go and select them within your micros because you have good enough contrast and it's easy to tell if the shape is clear, right? In the cases where things are smaller and a bit more heterogeneous, it can be a bit challenging to actually decide what is a particle, what is not a particle, what is a broken particle. So yeah, it can be a bit more problematic, and it can lead to bias from the user if you pick them manually. So it's probably a better idea to find a way to pick this automatically. But you can still try and do it manually. Now there's a lot of different software that will do automated picking, and this can be done in a reference-free or in a reference-dependent manner. Reliant will now is now able to do reference-free automated picking, and by using a Gaussian blob, that you need to adjust the height and the diameter of this blob to match your particles in your signal. And like Paula explained on her lecture, you can find a cross correlation between your reference, either of the two, and your image, and find the peaks in order to locate your particles. And if you have done your manual picking and run a quick 2D classification, you will have already some references that are better already than the blob, and you can use them for automated picking based on those references and be able to pick all your particles. And then again, word of caution, always check what you have picked. So go back to the micrograph, display the coordinates that have been selected, and make sure that in those coordinates there's a particle, and that the particle is centered as well. It could be that it's, if you have an elongated particle that is picking on one edge, and that's not good for reconstruction later. So make sure that things make sense. And in order to check for badly picked particles, Reliant has this sorting algorithm that will help you. So after running this, if you look for the high set scores, you will probably find a lot of false positives from the picking that you can discard. And again, if you don't have particles and you're picking with a reference that hasn't been low pass filtered to a reasonable amount, you will end up finding what you're asking for, and that can be very dangerous. So always low pass filter your reference to a reasonable value of 20 angstroms and pick with that and make sure that you can see the particles. Okay, so now we have the coordinates for all these particles in our images. And the next thing that we need to do is extract them. So box them and make a new image, extract this small part of the image into a new file. And you can do this easily within Reliance. So the only thing that you need to be aware of, the thing that you need to be aware of is the size of the mass that you're using and of the box that you're using and the mass for normalization. So to decide what the mass size is, or should be, you should be aware of what is the maximum distance within your particles, and you can measure this from the micrographs. And as a rule of thumb, I will say that, I think that's a common practice, that you will do 1.5 to 2 times the size of the box. And this works most of the times and for the initial steps of data processing. But remember that because of the defocus that we apply into a sample, the information is displaced. And you might need a bigger box in order to contain all this information. And this was already discussed by Richard and Peter Rosenthal a while ago. And what they say, they propose a formula here, and so you can go through it and decide how big your box would be. But this formula will give you a really big box, and that might give you a lot of problems during processing. So it's a good idea to start with a reasonable size for the box, and then later on at the later stages, increase it and see if things will improve, which might not be in all the cases. Okay, so now we have all of our particles, and the next step would be to run 2D classification in order to get an idea of the quality of our data set and to clean it up from badly picked particles or and false positives. So Shores already discussed how 2D classification works yesterday. So I'll just go through the different parameters that we can adjust in order to get it to work for our data set. And that would be the number of classes that we use, although probably using 200 for most of the cases will work. If you use many more classes, computation will take too long, and so that's not a reasonable thing to do. You need to decide whether to do CTF correction or not, which in most of the cases you will do. You need to decide the size of the mass, which would be related to the size of your particle, and it has to be a bit bigger than your particle. And then there's a couple of parameters that you could play with in order to get your 2D classification to work. One is this t-value that was discussed briefly yesterday, which for 2D classification, value of 1 or 2 is safe and works. And you can tune the resolution limit of the information that you're going to use during the comparisons. So 2D classification is a really good tool for assessing the quality of the data and to assess and to clean up the data set. So you will find that when you start running your 2D classification runs, you will see very good classes, or at the beginning might not be so good, but they look like a reasonable particle and all the thing. And this is a good opportunity to get rid of this kind of badly picked particles, Einstein from noise. So in this case, the data set was picked with a reference, and although most of the particles were picked where there were particles, there's some background noise that was picked with those references, and they come up as this Einstein from noise. So you should get rid of those very noisy particle-like things. And so this way we get a very clean data so that we can move on. And as I was mentioning, this is a good opportunity as well to assess the quality of the data set. So this is a bad one. And this can be done in early stages during your project. So you make your initial grids, you go to the microscope, collect a small data set, go all the way to 2D classification and find out something like this. So in this case, it was my first cryo-EM data set, well, not the first cryo-EM data set, but cryo-EM project. And after trying for a bit, we come to this point where we start to see some reasonable classes for the complex, but all the complex classes are in one orientation, and most of the particles that we have are individual subunits from our complex. So this was clearly problematic. And so the thing to do at this point was go back to the bench, improve the sample, improve the conditions to make to freeze the sample on the grids, and get to better conditions like the ones you see here, where now we have mainly complexes and there are more orientations, and this will now allow us to solve the structure. And whereas going for brute force, collecting lots of data for this sample might have never got us here. And this is just an example. I wanted to put a few slides on a recent data set for just as an example. So this would be the first, after picking the first 2D classification result. And because this is a small protein and it's quite heterogeneous, there's a lot of things that are picked that don't look like the thing that we're interested on. And so these classes don't look so good, but once you pick them and move to new runs of 2D classification, things start to look better. Also, another thing that I wanted to mention is that in order to speed up the process, you can limit the resolution that you're using, and you can bin the particles quite a lot, and this will speed up things, especially if your resources are limited. And because the information that is used for alignment is mostly the low resolution information, the low frequency information, alignment will still work, and you can speed up things like this. And then at the end, you can unbin your data or descale your data, go to your Dorina scale, and use all the information to get a better separation of your classes and find the full potential of your data set. Okay, so we've done 2D classification. We have a clean data set now. We want to go to 3D and make a reconstruction of our sample and of our protein. And in order to do that, as George mentioned yesterday, you need an initial model. And this might not be trivial. There's many different ways of attempting to get a 3D initial model. One would be if you will have a PDB or a map in the EMDB that is closely related to your sample. You could use this. For instance, if you're working with a ribosome, it's very likely you will have one that overall looks similar, and you can use that as an initial model. But you should always remember to low-pass filter it to avoid model bias. You can use 2D class averages from your 2D classification runs in order to make ab initio models. For instance, there's a couple of different algorithms within EMON that you can use. And recently, these stochastic algorithms that have been developed work quite well. And this is an example of simple working on this polymerase data that I showed you before, and the SGD, the stochastic gradient descent from CryoSparks, and now also in Reliant, making an initial model from randomly oriented particles from your data set. And then you can use this, we can use now this initial model to move into 3D classification and refinement. So for 3D classification, again, George already discussed how this works internally yesterday. And basically, we have one initial model that will be split into as many classes as you ask. It will be copied as many times as you ask for. And then particles are going to be aligned to all those different models that will evolve differently through the different iterations and will sort your data. And by doing this, you can separate different conformations within your data. So this is an example from one of our polymerase data sets where we can see that starting from the same model, we get different conformations of the data out. Now, there was also a question yesterday about how many classes should you use. And this is something that the user has to decide and find out, but you need to find out by yourself. So it's always a good idea to try different numbers and see how the data behaves. And it's definitely very sample dependent. So you can sense that value there and find out what is the reasonable value for your data set. Now, after you've done an initial classification of your data to get rid of bad particles that would probably be classified into classes that don't look like they have a reasonable reconstruction, you can move into 3D refinement. So in this case, this class will be a small number of particles that are probably not good and then went through 2D classification procedures, and you can get rid of them now and maybe go to 3D classification with the other ones. 3D refinement, sorry. So let's talk briefly about 3D refinement. So 3D refinement within Reliant is automatic, so is free from user inputs. It's done in a way where overfitting is prevented. And this is called the gold standard FSC. And what happens is that at the beginning of the refinement, the data is split into two halves, and they are refined against an independent model, and they don't see each other through the whole refinement. Only after, so after every iteration, every half, every reconstruction of the half data is compared through an FSC in order to estimate the parameters that Reliant will use through the refinement. And so in order to estimate resolution and the parameters that will tune during the refinement in order to align your particles. And you can follow the progression of this by looking at the run.outs, at the output from the refinement run. And then, so during the refinement, all these parameters will evolve, and then Reliant will allow, it will increase the sampling rate and will allow high resolution information to go into the refinement without overfitting. And at some point, there will be no improvement in angles or in resolution. And so the refinement will stop after these conversions. And after this happens, it will also write an unmasked half map for every half that we can use later on for post-processing. Okay, so after we've done this initial refinement, we can now go and do movie refinement and particle policing. And although we've already done movie motion correction with motion core or Ambler, and we've also corrected for dose for radiation damage with dose weighting. Doing this with Reliant will still improve the estimation of these effects. So in the first instance, what you have to do is run the movie processing job that will expand your particles into all the different frames that you could have collected, and align and do one step of refinement. So after doing this, you go into particle policing procedure, and what Reliant will do is use this translation estimation for every frame and feed a linear path through this. And this will help correct the movement of the individual particles. And it's done in a way where there's a weight with the movement of the neighboring particles are weighting also the movement of every individual particle, so things will move, so the signal is better. The other thing that we can do with with the particle policing procedure is correct for radiation damage again. And so what Reliant does at this stage is make a reconstruction for the two half maps for every frame, and do an FSC in between them, and use this to estimate a B factor for every reconstruction of every frame. And this is what you see here. And you can see that at the beginning, the B factor would be quite high, probably because of the initial movement of the sample with the initial electrons, with the first electrons coming through the sample. Then it will be a bit steady, and then it will progressively go down because of radiation damage. So by doing this, we can we can weight the information in a frequency-dependent manner for every frame, and correct for radiation damage across your movie, and improve the signal. And now this is because this is independent from your input. This is based on the data. Provided you have a good reconstruction, this will we've seen that this will improve the results as compared to what you can do with motion core. And this is just another example from a B factor plot with a sample that is a bit more noisy, but you can see that the behavior is still the same. Yeah, and so as I already discussed, I think so the question will rise as whether you should use motion core or policing in Reliant. I think you should use both, and would be the best approach, because having dose weighting from the very beginning is very useful for all the initial steps, but particle policing might help giving you an extra bit at the very end. So you should definitely try and use both. So after you've done particle policing, you have your shiny particles, and you can go in and do further classification in order to treat the heterogeneity within your sample and find the best subset of particles that corresponds to your different structures in your data set, and so you can then interpret the biology behind it. So I'm going to use this quite impressive classification scheme from Spliceosome, from Kelly in Kios's lab, because I think it really goes through all the different possibilities that you can use. And so you can see that at the beginning they start with 500,000 particles. After 2D classification, they get rid of some of the probably only false positive. And then after the initial set of the initial run of 3D classification, they go down to 140,000 particles. And this is probably just bad particles that got discarded at this point, that probably don't have the full complex or are disrupted, etc. Then they've done a refinement, particle policing, and they made a refinement again. And they got to this structure 3.7 angstrom resolution. But you can see that this is not very homogeneous through the whole map. And there's regions where there's barely no density, almost no density you can see, regions where the resolution is higher, etc. So how to account for all these different regions or improve the resolution in these regions? So what they've done first is do another global classification after the particle policing. And when they do this, they find that the data is splitting into different maps and with different subset of particles. And this was a question that was raised yesterday as well. So how to interpret this? I think this now comes to how can you, to your knowledge of your sample and what you know about it, you should open it in Chimera, look through it, and try to interpret what are the differences between them. You could also do, you could think about doing, you can subtract one map for the other, so to do, to look at the differences, a difference map, and try to find out what are the differences. But I think the best way to do it is to just look at them in Chimera and try to understand what are the differences. So in this case, they have two main classes, and what happens is that one has a closed pocket and another one has an open pocket. And so this is biology, is relevant for the biology, and therefore they refine both and then interpret the maps for both conformations. But you can see that in this map, there's still regions that are quite flexible. So in order to deal with this, what you can do is go and treat each region from this map as an independent region, the independent subset of the map. So you can do this in many different ways, and probably the best way, once you have a high resolution reconstruction like they have, is to use focus refinement with signal subtraction. And what this means is that you would get your map and subtract the region you're not interested in order to get images that only contain the information that you want to compare and align. And we can go in detail through this later on if anyone is interested. And by doing this, you get better images for this focus refinement and classification. So they've done this for the different parts by subtracting. So in order to look at the head, they subtract foot, body, and arm. In order to look at the body, they subtract the other three, and so on. So by doing this, then they can now use a mask around this region that they keep, and do a refinement and improve the angles for this region, and therefore the resolution of the reconstruction, and make a model for that, and the same for the other parts. But so this is done for those three parts, but then the arm is actually quite small in order to do refinement after you do the signal subtraction. So there's no signal in this region to do a refinement, and so what they do is do the signal subtraction and then just do classification around this without aligning. And this allows them to select a subset from those particles that has a better density, and then go back to a bigger region and do alignment and improve the signal in this region that still doesn't go to as high resolution as the other ones, but reasonably good to interpret the map. So I think this is a good example of how you can use the different strategies for classification to get the most out of your data, and you should really explore the different possibilities and in order to find out what is the behavior of the sample and get the most out of it. This is another example from our polymerase data set, and I think it's quite illustrative of what can happen. So this is a 220 kilodalton complex, and what I'm showing here is the range of movement that the particles are undergoing when you're freezing them. So this is 3 different proteins that are bound by a very only by a linker in between them, and so the relations in between these different domains are quite flexible. So what I've done is from the reconstruction at 7.2 with 11,000, actually when I did this it was a bit higher number, I classified it into 10 different classes, then feed a model to each of those classes, align to one of the proteins, and then play the movie through them so you can see the range of movement. So what you can do now in order to account for this movement is divide, like I just told you, the sample, your map into different domains and refine the angles individually. So you can improve the resolution from 7 to 6 for these 2 regions. The reason why you cannot improve it further is because there's still regions that will move independently within this, but if you will now go into smaller, you won't be able to align them. So you're limited by the size of the signal, size of your molecule and the signal that it provides. Okay, so now you've, after doing refinement, in order to prevent overfitting, when Lion does the FSC comparison between the 2 half maps in order to estimate resolution, it's not going to use a mask to calculate this FSC. So the estimation of the resolution is going to be underestimated during refinement. This doesn't affect the reconstruction or the estimation of the angles because this is driven mainly by lower frequency components. But in order to get the best reconstruction that you can get from your data and the proper estimation of resolution, you can use a mask at this point, and you can do this through post-processing, which is basically using a mask for each of the half maps and calculating an FSC that will allow you to estimate your resolution properly. And because you're using a mask, you have some artifacts due to convolution from strong low frequency components that creep into high resolution components. And Reliant has implemented this phase randomization protocol to get rid of or fix mostly these problems with the masking effect, especially when you use a very tight mask. And the other thing that you can do during post-processing is sharpen your map. And you need to do this in order to actually see what are the high resolution features. So this would be an unfiltered map and a filtered map after post-processing. You can see that the resolution of this map is around 3.5, 3.7. Before filtering, you cannot see any high resolution features. After that, you can see side chains and these helix, etc. And the reason why you need to do this is because during the whole process of imaging, acquisition of data, processing of data, the high resolution frequencies are dampened, and this follows. You can estimate this as a B factor that you can apply in order to bring this to sharpen them up and bring this up again. And then last but not least, we should how to validate, how do we know if the structure is right? So I think the main thing is common sense. So if your reconstruction is around 9 angstroms, you should be able to see secondary structures as alpha helixes, and beta strands will already be visible at 4.8. So be aware that there can be many problems during your reconstruction process that can lead to an estimation of resolution that might not be right. So you need to make sure that what you see is actually, it correlates well with the estimation of resolution that you have. And if the resolution is not good enough, or you cannot validate your reconstruction this way, a tilt pair validation is a very good way of making sure that your structure is correct. And this is done by collecting tilt pairs during data collection. So basically, for a few images, you collect an image, a normal image, and a tilted image are, let's say, 20 degrees. And you know this tilt. So then you can feed this data, these particles, into the data set, make your refinement, and then plot the angles assigned to these previously tilted particles and see if they are actually properly assigned. And by doing this, you can find out whether the reconstruction process is working properly. And you can visualize this with this tilt validation plot, tilt pair plot. Also, you should make sure that you have the right handedness, and this you can do with a tilt pair as well. But if you have high resolution enough, you can do it with helices. You can do it if you have a part of your protein where you have a crystal structure for it. You can find out what the hand is, etc. And then again, make sure that you can see particles, and then the reconstruction you're making makes sense. And I think it was a bit quick, but that will be all. I hope this was a good overall view of all the different steps that you need to go through and what are the important steps in each of them. And I wanted to mention briefly that one thing that you can do is already automate this during data collection, and this can now be done quite easily through Reliant with the scheduling different types of jobs. So while you're collecting data, after every image that comes out of the microscope, you can already do motion correction, CTF, picking automatically, and feed it into 2D classification iteratively. So when you come back the next day, you can already start to select your good images and start with 3D classification. So that will speed up the whole process. And yeah, and I'll take any questions. Thank you.